In this lecture, I'm going to briefly go through the Euler equations of gas dynamics and talk a bit about how what the Hugoniot loci and integral curves look like and how we can project the phase space, which is a three-dimensional space, to the PU plane, the pressure velocity plane, in order to solve the general Riemann problem for the Euler equations. There's a notebook in our Riemann Problems in Jupyter Solutions book on the Euler equations that has some more examples of Riemann solutions and widgets that you can use to play around with what the solution looks like, for example. So I recommend taking a look at that as well. Recall that back in Chapter 2 we looked at compressible gas dynamics a bit in the context of the system of conservation laws for density and momentum alone, assuming that the equation of state could be written as a function pressure as a function of density alone. And now that we've looked at the shallow water equations, you see that there's a very similar structure here. In fact, if you replace rho by h, the depth in the shallow water equations, then these are exactly the same equations as the shallow water equations if we use the equation of state P equals 1/2 g rho squared, or 1/2 g h squared is the hydrostatic pressure in the shallow water equations. But we also looked at this in the case of isothermal flow and isentropic flow, where the pressure is a simple function of density, and you get a structure of the Jacobian matrix that's identical to the shallow water equations in those cases. When we go to extend this to look at also conservation of energy, then there's a number of new variables that come into play. And I'm not going to try to give a description of the physics of gas dynamics or the thermodynamics. There's a little bit more information in the book, but there's many other resources that are much more authoritative on this subject than what's in the book. But here I've just summarized a few of the new things that come into play. And for the purposes of this lecture, I'm going to kind of focus on the mathematical structure and also focus on the case of an ideal polytropic gas, for which some of the quantities in blue here take a special form that makes things a little bit simpler than the general case. So in addition to the density, velocity, and momentum and pressure that we've seen before, we also have to look at the energy, and the total energy, capital E, is split up into internal energy, which relates to the vibration or other forms of energy within the molecule, and the kinetic energy due to the fact that the molecules are moving. Total energy is the sum of those two. And we can also define things like the temperature, capital T, which for the case of a polytropic gas, the basic assumption is that the temperature, or that the internal energy, is simply proportional to the temperature, and the constant of proportionality is C sub V, the specific heat at constant volume. And then with that assumption, you can define, there's also a specific heat at constant pressure, Cp, and the ratio of those is this quantity gamma, the adiabatic exponent for a polytropic gas, which depends on exactly what kind of gas it is. It ranges between 1 and 5/3 typically. Gamma can also be expressed in terms of the number of degrees of freedom in a gas molecule. And gamma is 5/3 for a monatomic gas. It's 7/5 rather, or 1.4 for a diatomic gas like oxygen and nitrogen that make up most of our atmosphere. So often we assume gamma is 1.4. And then another quantity that's going to be quite important is the entropy, which for a polytropic gas can be written in terms of the adiabatic exponent gamma. In this form, it's basically some constant times the log of P divided by rho to the gamma. So it's sometimes described as the amount of internal energy that's available to do work in a system, and is a measure of the amount of disorder in the system. So with those variables, a polytropic gas is one for which the internal energy is P divided by gamma minus 1 times rho, and then the total energy is the internal energy plus the kinetic energy. and we can solve from this relation between P rho and the internal energy. We can solve for what the pressure is as a function of the total energy and the mass and momentum. It's just gamma minus 1 times the internal energy, and that can be written, therefore, as the pressure is some function of the conserved quantities, rho, u, and E, and that's the equation of state for an ideal polytropic gas. By contrast, when we looked at isothermal flow, there we were assuming the temperature was constant, and so from that we can find that the pressure is some constant times rho. Earlier we called that just a squared times rho, and so that's the equation of state for an isothermal flow. For isentropic flow, if we instead assume the entropy is constant, then that again gives us a relation that gives us P as a function of rho alone. But the full system of Euler equations in one space dimension are a system of 3 equations. In 2 dimensions, we'd have 2 components of momentum, so we'd have a system of 4 equations, and in 3D we end up with a system of 5 equations. But we'll focus here on the one-dimensional flow, where the flux is given by the vector here on the right. So we have the usual conservation of mass and momentum, have the same fluxes as we've seen before. Conservation of energy, there's an advective term that energy is advected with the flow, so we expect an E times U in the flux, but then there's an additional term that corresponds to the pressure term that shows up in the conservation momentum. We have also U times P showing up in the flux of energy in the full Euler equations. But it's not too much more complicated than what we've seen before. And if we calculate the Jacobian, the derivative of f with respect to the 3 conserved quantities, rewriting this f in terms of those conserved quantities, then you can compute the eigenvalues and eigenvectors. I'll show those on another slide a little later. But of particular importance is the fact that the eigenvalues turn out to be, as we might expect, u minus c and u plus c are eigenvalues corresponding to sort of the acoustic waves. But there's a third eigenvalue that comes in when we look at this system of 3 equations, and the third eigenvalue is always in between the other 2, and it's just equal to u, the fluid velocity itself. So we have sound waves which can propagate at speed plus or minus c, the speed of sound relative to the fluid velocity, but then there can also be something transported at the speed of the fluid velocity itself. And the sound speed in general is the square root of the derivative of pressure with respect to rho when calculated at constant entropy, because sound waves are isentropic. And for a polytropic gas, that just reduces to being the square root of gamma p divided by rho. So with that definition of C, those are the eigenvalues of the Jacobian matrix. It's a little easier to look at, though, if we think in terms of the primitive variables for a moment instead of the conservative variables. So the primitive variables are sort of the more natural physical quantities, the density, velocity, and pressure. And if you rewrite things in those forms, we can rewrite the conservation laws after some manipulation. We can rewrite it as a quasi-linear system of equations. So this is of the form qt plus the Jacobian matrix f prime of q times qx equals 0, but rewritten in quasi-linear form. So the Jacobian matrix in terms of these variables differentiating with respect to rho, u, and p has a relatively simple form, but this Jacobian matrix depends on the variables, rho, u, and p in this case, and so this is a quasi-linear equation. It's qt plus f prime of q, qx equals 0, so it's not in conservation form. So this isn't the right form for figuring out shock speeds, for example, using the Rankine-Hugoniot conditions. But it can be used to calculate the eigenvalues and eigenvectors. The eigenvalues are exactly the same as we'd expect, regardless of what variables we use. The speed at which waves propagate are the same, u and u plus and minus c. But the eigenvectors, r1, r2, and r3, depend on the set of variables that we're using. So these are eigenvectors in terms of rho, u, and p. And one thing you note is that row R1 and R3 look fairly similar, and those again will correspond to sort of the acoustic waves. R2 is particularly simple, and it shows that there's variation in density, but not in U or P. And that's a very important fact about this third family of waves that we introduce when we go to the full system of equations, that typically the two waves have variations in density, but not in velocity or pressure. And we'll use that fact to good effect in figuring out what the general Riemann solution is. So even though we'll have to go back to the conservative form to calculate what the Hugoniot loci are, for example, the fact that U and P are constant through two waves will be very useful. And if we calculate the gradient of lambda inner product with the eigenvectors, which we looked at before for the shallow water equations to determine whether that each field in that case was genuinely nonlinear, when we do it for the Euler equations, what we find is that the one waves and three waves are genuinely nonlinear because this inner product of the gradient of lambda with R is a half gamma plus 1 in both cases, and that's always non-zero. Gamma is just some constant. So we have genuine nonlinearity of the one waves and three waves, but the two waves are linearly degenerate because the gradient of lambda is always orthogonal to the eigendirection. So if we consider a Riemann problem, and if we go back to the conservative variables for the moment so that we can talk about the Rankine-Hugoniot jump condition, then we can see that this two-wave family across which the pressure and velocity are constant also satisfies the Rankine-Hugoniot conditions if we choose an appropriate speed for the discontinuity. So if we assume that the pressure in our left state and right state are equal, and that the velocity in the left state and right state are equal, and call that common value simply u, then if we look at the Rankine-Hugoniot conditions, which in general say that the shock speed, or the speed at which a discontinuity propagates, times delta q has to equal the jump in f, then with these assumptions, the left-hand side here, s times the jump in q, becomes simply s times the jump in rho, u times the jump in rho, and the jump in e, using the fact that u is constant in the left and right states. And the right-hand side, the jump in f, becomes u times the jump in rho, u squared times the jump in rho, and u times the jump in e. Everything else drops out when we look at the jump in f. If p and u are constant, then the terms that involve p drop out, and the other terms we can factor the common u out of and have this expression. And then if we set s equal to u, the left and right hand side are equal here. So what we see is that we can satisfy the Rankine-Hugoniot jump conditions provided we take s equals u for any jump in density, delta rho. So that says that we can have a discontinuity that propagates as long as these conditions are satisfied, that the pressure and velocity are constant across the jump, then we simply have a discontinuity that propagates at that speed u for any jump in density. And that's very useful in solving the Riemann problem in general. Also notice that this doesn't make any assumptions about the equation of state. We've just used the jump in E here. So it doesn't really matter what the equation of state is. It's always true that this two-wave family has these contact discontinuities where you have a jump in density but not a jump in pressure or velocity propagating with a speed that's equal to that common velocity. So here's what the Jacobian looks like if we take that conservation form and differentiate that flex function we just looked at with respect to the conserved quantities, rho, u, and e. And as I said, it looks much simpler in the non-conservative form, but to calculate the Rankine or the Hugoniot loci, for example, we would have to use the conservation form. And also to calculate the integral curves and how a rarefaction wave varies through the integral curves. It's the integral curves relative to these vectors in conserved quantities that we might want to use. There's also this concept of Riemann invariants that we looked at for the shallow water equations, and for the Euler equations we have a system of 3 equations, and it turns out that for each wave family there are 2 Riemann invariants. So if we look at a one wave, for example, then the 2 Riemann invariants are the entropy S and this other quantity, where this square root of gamma p over rho is the speed of sound, remember. And in the 3 waves, we also have S, the entropy, as a Riemann invariant, and a similar expression, but with a minus sign instead of a plus sign, for the other Riemann invariant. And then for the 2 waves, as we've just seen, the Riemann invariants are the velocity and the pressure, which are constant through any 2 wave. But the fact that the entropy is constant through any 1 wave or 3 wave, at least if it's a smooth, simple wave in the 1 wave or 3 wave family, means that we expect in those families that we have smooth, simple waves through which the entropy is constant. And so in particular, if we look at just a linearized acoustics wave, which has very small variations in the pressure and the density and the energy, the entropy we would expect to be constant through those waves. And so as we've seen before, when you look at linearizing things, isentropic is the proper assumption for acoustic waves. And then, as we've already noted, across the 2 waves, U and P are constant, and so any simple wave in the 2-wave family would have U and P constant, but we also checked through the Rankine-Hugoniot condition that in fact any discontinuity in the 2-wave family also has U and P constant across it. Whereas a discontinuity in the 1-wave or 3-wave family does not have the entropy constant, because those fields are genuinely nonlinear. So discontinuities behave differently than smooth flow. And in fact, the entropy can be used as an entropy function in the sense we've talked about before, to determine whether shock waves are physically correct or not. Although in the physical gas dynamics case, the physical entropy actually increases across a shock wave rather than decreasing as our mathematical entropy functions did before. So if we look at a general Riemann problem for the Euler equations, well, we would have jumps in all 3 variables, but if we look at a simple case where we take the velocity to be 0 on both sides, that gives us what's called a shock tube problem, if we assume that the velocity is 0 on both sides. So you can think of this as a tube of gas that has a membrane separating high pressure gas on one side with lower pressure gas on the other side, say, but with 0 velocity in both cases. And then at some initial time you break that membrane and see what happens. And this kind of shock tube has actually been used a lot in experimental studies to understand the properties of gases. And it's analogous to the dam break problem for the shallow water equations, where we assume 0 velocity on both sides, but a jump in the fluid depth in that case. And what you see is something very similar to the dam break problem. You see that starting with the high pressure on the left, lower pressure on the right, you get a shock wave that moves to the right, which would be a 3-wave in this case, a rarefaction wave moving to the left, which would be a 1-wave. And then in the case of the full Euler equations, we also have a 2-wave in between, which is a contact discontinuity, where the 2 fluids are in contact with each other. And that's indicated here by the change in color. And so at some later time here we have a contact discontinuity where, notice there's no jump in pressure, and there's also no jump in the velocity. The fluid velocity is the same on both sides of this contact, but there is a jump in density now, in addition to being a jump in the color if we were augmenting the system with a color equation for some transported scalar quantity like we had in the shallow water equations. Or if we look at it in the xt plane, we get a picture like what's up here on the upper left. And we now expect sort of 2 intermediate states. This QL star is the state shown here. QR star is the state down below. And notice that P star and U star are the same in both of those states. It's only the density that's different between the two states. So notice also that it's a similarity solution, just as in the case of shallow water equations or any nonlinear conservation law. We expect the solution to this particular Riemann problem, where the data is piecewise constant with a discontinuity only at x equals 0, to be then a function of x over t alone. And so we'll see how we can calculate sort of this exact Riemann solution in a moment, but this also suggests that we could maybe replace this wave with just a propagating discontinuity, as we did in the scalar conservation law case, and use something like a wave propagation method to implement this numerically and apply limiters to get high resolution methods. So we'll look at that a little later, and also the idea that we can, when we replace a rarefaction wave with a single jump discontinuity, that's really an approximation to the Riemann solution in many cases. And so that's one form of an approximate Riemann solver. There's also even simpler approximate Riemann solvers that we'll look at also that would replace maybe this Euler equations with three waves with only two propagating discontinuities, for example. But in a future lecture, we'll look at approximate Riemann solvers. But for the moment, we want to talk about how would you actually compute, in principle, the exact solution of this Riemann problem. And so to do this, we use the fact that, as we've seen, across a contact discontinuity, a two-wave, any jump in the density is allowed. And so it turns out we can kind of project the three-dimensional phase space onto the PU plane. And I'm going to work in terms of the primitive variables, P, U, and rho, the density here. And so you can think of this plot as being a projection of the three-dimensional space on the 2D space, or you can think of rho, the density, is varying in the third direction into and out of the plane, but we're sort of looking at this one projection. And what we'll see is that we can come up with formulas for how the velocity varies as a function of pressure alone. Of course, the density will also be varying as a function of pressure, but if we project into this plane, then that variation of the density sort of disappears. And so for any given states, we can find the variation of u as a function of pressure. And I wrote it as phi of p here, same notation I was using for the shallow water equations. What we'll see is that there's one function of p to the left of a point and a different function of p to the right of the point in the phase plane, because we have to decide also whether we should be using a shock or a rarefaction wave in each family. And so there's really these four different waves, one wave integral curve, one wave Hugoniot locus, but also in this case the three-wave integral curve and the three-wave Hugoniot locus that all sort of come into play. So if we have a particular state Q left, and let's say this is Q left for the moment, then we want to find, and this is QR, say this other state up here, the idea is to find in this PU plane the appropriate curves to use so that we can connect QL through a one wave to some state QM, and then connect that state QM through a two wave to QR. So if this is the orientation of QL and QR, then QM would be the state here where one of these one-wave curves coming from QL intersects the appropriate three-wave curve coming from QR. Or of course, if I switch these states and called the one on top QL and the one down here QR, then we would need a one-wave connecting QL to some intermediate state over here, and then a two-wave would connect that state to QR. And once we found that intersection in the PU plane, then since we also have expressions for how rho varies along each of these curves, once we found the intersection P star, U star, the middle state, we can then find the rho L star and rho R star, the two different values along the two different curves for the density. But they would in general be two different values of density. We would have to follow the one wave curve from Q left in the three-dimensional space, and the three-wave curve from Q right in the three-dimensional space, and those would lead to the same pressure and velocity at the intermediate state, but to different densities. So to compute the one wave, again, as in the case of shallow water equations, we use we have to calculate the integral curves of the eigenvector R1, but it's greatly simplified by the fact that we know two different Riemann invariants, two functions of the variables that are constant along any integral curve. In particular, the entropy is constant, and from that we can calculate that the density along any integral curve has to be given by this expression down here. If we know the density and the pressure in the left state, for example, then we know the entropy all along this curve, and from that we can calculate the density anywhere along this curve. So at some other point for some other pressure, we can calculate the corresponding density from the curve, from the formula down here. And using that, we can, and also using the fact that this other quantity, u plus 2 over gamma minus 1 times c, where c is the square root of gamma p over rho, is constant, and replacing rho here by this expression down here so that we can also write this as a function of p alone, we end up with this expression for how u varies as a function of p along this integral curve. And that's the function that we'll call phi sub L of p, because this is only valid if p is less than or equal to pl. And that's because of the way the eigenvalues vary along the integral curve. In order for this to be a state that we can connect to the left state as a potential middle state, we need the eigenvalue, lambda 1, to be increasing as we go from state QL to one of these states on this integral curve. So that determines how the pressure has to vary in order to respect that. And then we can do exactly the same thing for the three waves. We have a different set of Riemann invariants, the same entropy, but the other one has a slightly different expression. In particular, it has a minus sign here, and so this I think should actually be a minus sign. It's a typo, because the other Riemann invariant on the three wave is u minus 2 over gamma 1 times c. And then if we look at shocks instead of rarefaction waves, we have to look at the Hugoniot locus. And remember, the Hugoniot locus through a given point is the set of states we can connect by another state that satisfies the Rankine-Hugoniot condition for some scalar speed s. And it's more complicated to figure out how to solve those equations. Even in the book, I don't go through the details, but there's a reference there to where you can find the details. But the main point is that we, again, come up with an expression for how u varies as a function of the pressure. So as a function of the pressure, and for a given left state, so the PL, rho L, CL, UL are all based on the left state, this gives us how u varies as a function of p, and that's the function phi sub L of p, defined now for p greater than or equal to PL, the other direction than where the integral curve was valid, because it's in this direction that we can connect things with a discontinuity that both satisfies the Rankine-Hugoniot condition and satisfies the entropy condition, which means that the characteristic speed has to be smaller in the state u, or in the state pu, than it is in the state ul pl. And again, we can eliminate rho so that we get u only as a function of p, and then there's another formula that gives the variation of rho along this curve, which is given here. So once we've found an intersection, then we can evaluate also what rho is at the intersection point. And you can do similar things for the three wave and get an expression for how u varies as a function of p for p greater than or equal to p right. So again, here's what these curves look like when we project them onto the PU plane. the formulas that I just showed, just plotting as a function of u as a function of p, which has sort of implicitly used the fact that rho is also varying along these curves. So it's important to remember that these are projections onto this plane, and exactly what these curves look like depends very much on what the value of rho is. So if this is our point q star here, then p star is 3 and u star is 2, but there's also a rho star which isn't shown in the plot except in the title up here. And if I change the value of rho star, then the curves would change because they would be really different curves in the three-dimensional phase space that we're projecting onto the PU plane. So if I change from rho star equals 3 to rho star equals 1, for example, then here's how those curves change. So the curves look different. They both go through the same p equals 3, u equals 2 point, but they're projections of different curves in three-dimensional space because they go through different points in 3D space. So to solve the Riemann problem, we would look at for intersections in this PU plane. And here I'm showing a figure from the Euler notebook in the Jupyter Solutions book, because I also wanted to point out what the color scheme is we use there, which is slightly different and isn't really explained in that notebook. So what's being used here is that, first of all, the left state is this symbol with sort of a left pointing arrow. The right state is the one with the right pointing arrow. And the middle state that comes out of the Riemann solution is the dot. And in these plots, blue corresponds to integral curves and red corresponds to Hugoniot loci. So for this particular choice of states, because we have to move in the direction to the left of this Q left with smaller pressures, it turns out that the correct solution is a rarefaction wave in the one family, and then going from QL to Q middle, and then going from Q middle to Q right, it's a shock wave. For this particular set of data, which is up here, it was a density 3, velocity 0, pressure 3 on the left, and density 1, velocity 0, pressure 1 on the right. So this is a particular shock tube problem where we had a higher pressure equals 3 on the right, pressure equals 1 on the left, the same velocity on both sides, and also a particular jump in densities. This is what's often called the SOD shock tube problem after Gary Sod, who used this particular example in testing a bunch of numerical methods back in the early days of computing this kind of solution. So again, the way we would solve this Riemann problem in practice is we define these functions phi L of p, which is corresponds to integral curves on one side of p star and Hugoniot loci on the other side, and we define phi r of p similarly for three waves. For three waves, phi L was defined based on one waves, either the Hugoniot locus or the integral curve. Phi r is defined based on three waves, and then we want to find this point in the middle here that lies on both of these curves, so we can do that by requiring that phi L of p, which is u in the middle state, should equal phi r of p, also u in the middle state, or subtracting those and setting that to 0, we get a nonlinear scalar equation that we can solve for the pressure in the middle state by applying Newton's method or some other nonlinear solver. And then once we've solved that, we can just evaluate either phi L of PM or phi R of PM. Those two should be equal now, and that's the value UM, which gives us this intersection point. But then there's some other relations that tell us how rho varies along integral curves or shock curves, and so depending on whether each of these is an integral curve or a Hugoniot locus, we can determine what the corresponding rhos are on the two sides of the contact discontinuity. And again, these two curves are projections of curves from 3D space. So if we looked at it in 3D, the red curve is displaced from the blue in the rho direction, and there's a contact discontinuity that connects the two in that third direction. So really in phase space, there's three waves. There's initially the one wave connecting the left state to this point, which has some rho associated with it. Then there's a two-wave that goes into or out of the page, which is just a straight line connecting two different values of rho with the same p and u. And then there's the three-wave connecting that second point to the right state. So this is a projection of a set of three curves in the 3D phase space. And if we look at it in the xt plane, we get the figure up at the top, or if we look at it at a particular time, then we see the shock wave moving to the right, the rarefaction wave moving to the left, and this contact discontinuity moving at the intermediate speed, which shows up as a jump in density. But if we look at the same location in the velocity or the pressure, the solution is continuous there. There's no jump in those variables across the contact discontinuity. And again, in the Jupyter Notebook, you can play around with this and change the left and right state and see how the structure of the solution changes. Oh, those plots that I showed and all of the plots in the book and in that notebook are using kind of non-physical values of pressure and density. You might wonder, what does a density of 3 mean? And if we really want to relate this to actual air, it makes more sense to plot these things around the values of pressure and density that are relevant for atmospheric air. So a standard sort of atmosphere is where the temperature is at 20 degrees Celsius, the density is 1.225 kilograms per cubic meter, and the pressure is around 101,325 pascals, or about 101 kilopascals, which is defined as 1 atmosphere, as another unit for pressure. So at a pressure of 1 atmosphere and at atmospheric conditions, the speed of sound is about 340 meters per second. And here's what the curves look like if we kind of zoom in around 1 atmosphere. Actually, this isn't terribly zoomed in. This is going from about half an atmosphere down here to 2 atmospheres up here. The dot is at 1 atmosphere. And one thing you notice is that the integral curves and Hugoniot loci lie right on top of each other in this plot. They're really very similar when we look at this scale of things. And also they're looking fairly linear. And then if you think about linear acoustics, then we're even more zoomed in around where that dot is. In fact, I think the threshold of human hearing is something like 20 micropascals. So 10 to the minus 6 pascals, something on that order. So everything that we think of as sort of ordinary acoustics and sound waves is kind of down here covered up completely by that black dot. So if you really zoom in to another order of a million here, then you would see sort of the regime of linear acoustics, and things are really very linear in that regime. If we zoom out a little bit more, though, and go from, say, 0.1 atmospheres to 10 atmospheres in pressure, then you start to see the nonlinearity a bit stronger, and also the deviation between the integral curves and Hugoniot loci. But this is getting up to very extreme pressures and densities. Although if you're looking at, for example, supersonic flow, modeling flow around a supersonic aircraft or whatever, since the speed of sound is about 340, that's up around here. So of course everything varies as you start changing things around between atmospheric pressure and that sort of speed. But still, you can use the Euler equations with the polytropic assumption, gamma equals 1.4, for doing a wide range of aerodynamics problems. It's really only when you get into sort of very low pressures or very high pressures that you have to use special equations of state or other equations altogether. Once you get down to very low pressures and densities, to what's called rarefied gas dynamics, like out at the edge of the atmosphere, if you were looking at re-entry of a spaceship or something, then the Euler equations really aren't valid at all, because the particles are so far apart that ordinary pressure doesn't make sense. The molecules aren't colliding with each other very much. So you typically have to go to other sorts of equations altogether in those cases. Oh, one final comment to make about these curves. They look somewhat different from what we saw with the shallow water equations. If you remember the phase plane curves that we were looking at there, we had plots like this for the Hugoniot loci and integral curves, and if we looked at other points in the plane, the one wave Hugoniot loci or integral curves looked like this, for example. We got sort of this family of things, and in the two-wave family, we got things that looked like this, and they all came together here at the origin, whereas the plots we were just looking at for gas dynamics, they were not coming together at the origin at all. But the main reason for that is that for shallow water equations, I was using the conserved quantities, so the depth and the momentum is h times u. So as h goes to 0, all of these curves go to hu equals 0 as well, assuming the velocity is staying finite. Hu goes to 0 as h goes to 0. So this is the fact that everything comes together at the origin here is kind of related to the fact that we use the conserved quantities. Whereas in the Euler equations, we were looking at the pressure and the velocity, not the momentum. And similarly, if we take the shallow water equations and just replot these same curves, but divide by h in our plots so that we're looking at h and velocity, then you get something that looks more like the curves for gas dynamics. Although in this case, looking at h very small, h going to 0 even, is more physically relevant because the shallow water equations with 0 depth does make sense. And in fact, if you look at flow intruding over dry ground, modeling a flood or a tsunami coming on shore or something like that, the shallow water equations are often used with dry states on one side and wet states on the other, and you have to deal with that Riemann problem. That'll be the subject of a later lecture. But the main point of this lecture was that what we did for shallow water equations in the last couple of lectures, you can do something very similar for the full system of Euler equations, using heavily the fact that the two-wave is this contact discontinuity that has a linearly degenerate structure, which makes it much easier to solve the Riemann problem than it would be for a general system of three equations.